This lecture explains how a star follows a predictable path on the HR diagram, a path almost completely determined by its mass. When a nebulous region of dust and gas collapses to form a star, there are three possible outcomes. If the mass is less than 5% of the sun's current mass, then the core temperature never reaches the critical 10 million Kelvin needed for fusion. It becomes a failed star called a brown dwarf. If the mass is greater than 8 solar masses, then a star is a high-mass star. The evolution of a high-mass star is the subject of the next chapter and learning module. If the mass is greater than 0.05 masses and less than 8 solar masses, then the star is considered a low-mass star. Low-mass and high-mass stars make predictable paths as they collapse and evolve toward the main sequence. Low-mass stars spend most of their lives as main sequence stars. Figure 12.14 shows the predictable path of a low-mass star when it runs out of fuel. On the HR diagram, it spends the majority of its life on the main sequence. Eventually, the hydrogen runs out and it evolves off the main sequence, making a circuitous journey to the region of red giants, then swings wildly to the left, reaching very high temperatures, and suddenly downward to the region of white dwarfs. In Chapter 10, we learned how luminosity can be measured directly when distance is known through parallax, and how mass is measured from binary star systems. Based on observations of stars with well-known luminosity and mass, astronomers found a power law relating mass and luminosity. The data are presented in Figure 12.2. Luminosity is proportional to mass raised to the power of 3.5. The exponent 3.5 is an average value over a wide range of main sequence star masses. The mass of the star determines almost everything about the star's life. Where it will be on the main sequence, what its mass, luminosity, temperature, spectral type, and size will be throughout its life. The path it will take as it runs out of fuel, and its eventual state when it dies. This pie chart from Pearson Educational shows the distribution of masses of main sequence stars, as determined by surveying the local solar neighborhood. The vast majority of stars the size of the sun and smaller. The vast majority are stars the size of the sun and smaller. For main sequence stars, the luminosity of a star can be determined from its stellar classification. The mass can be determined from the luminosity. Table 12.1 shows the luminosities for spectral types O5 through M5. Recall that 5 designates a cooler temperature than 1 on spectral type. In Chapter 11, we worked through a back-of-the-envelope calculation to estimate the life expectancy of the sun. We can now show that the lifetime is proportional to the ratio of luminosity to mass. Because of the mass luminosity power law, with algebraic rearrangement, we can write the lifetime of any main sequence star as being equal to the product of the lifetime of the sun and the star's mass in solar masses raised to the power of negative 2.5. From this, the lifetime of the main sequence star is calculated. This brings us to a completely counterintuitive finding. The most massive stars have the shortest lifetimes by several orders of magnitude. Notice that the bright blue-white O-type stars survive only about 360,000 years, whereas the sun will have a lifetime of 10 billion years. Smaller, cooler stars have lifetimes on the order of 490 billion years. Just a reminder to pay attention to the vocabulary alerts in the textbook. In Chapter 11, it was pointed out that astronomers sometimes refer to proton-proton fusion as hydrogen burning, even though no chemical changes are taking place and no oxygen is consumed. Keeping with that metaphor, the helium that results is sometimes referred to as helium ash. Figure 12.3 shows the radial cross-section of the fraction of hydrogen in blue to the helium in purple for 3 sun-like stars. To the left represents the hydrogen to helium ratio of the sun when it formed about 4.3 billion years ago. The center plot is the sun today, with the buildup of helium ash at its core, and a depletion of hydrogen in the core. Today, roughly 35% of the mass in the core is hydrogen, although the outer shell, called the radiative and convective zones, have the same composition as the sun when formed. In 5 billion years, there will be no more hydrogen at the center, and not enough left in the core for fusion to continue. At that point, the sun will run out of hydrogen and leave the main sequence. In summary, stars follow a predictable path on the HR diagram that is based almost entirely on the mass, and to a very small extent on their chemical composition. As the star collapses, the position on the HR diagram smoothly progresses to its place on the main sequence. The lifetime of the main sequence stars can be determined from the mass, and surprisingly, the most massive stars have the shortest lifetimes. When the fuel in the core is gone, the star moves off the main sequence.